Here is a simply supported structure, portal frame, how we analyze the deflections as the center of the beams. When it is a portal frame, we have to consider a 1 meter length of the structure in both sides, and then so that applied to work out the moment at the center. The way to represent it is like this. When we have the two columns supported, when the beam at the center, the UDL, the dead load, and the live loads are collected through the slab into the beams, and the amount of load that is collected is 1 meter center to center from the previous beams. We have to work out the mid span. In this case, I put 1 meter because that's what I am going to consider. It could be 5 meter or 4 meter, depend. If the lengths between the two beams are longer, then we have to take half of it, and then we take one strip of 1 meter and work out the dead and live load. And then using a Euro code or British code, we can calculate the bending, the total load to use for calculating the bending moment. The simplest way of representing it this way. So that is the first column that we saw in the portal frame. That is the second column, and W is calculated. How? Of course, we have to use the live load and dead load. We have to work out what kind of dead load and live load is going into the slab, which is 1.35 dead load plus 1.5 live load. That will work out the small w. In our case, we work out around 4.8 kilonewton per meter square. Now, if we want to work out the deflections as the center of the beam, what we have to do is we have to calculate the bending moment diagrams and then work out the formula. So if we take a cross section at this point, we have A, and the load is here. If we call this distance X, there is a moment, shear force in both directions. We know VA is equal to VB, which is here VA, VB, they are WL over 2. So this spot, that is WL over 2. Then we've got the X distance. There is this load, which is W times X. We apply that at the center to cause a bending moment as cross sections. So if we call this MX, MX is equal to, taking a sign convention, that will be plus, which is WL over 2 times X minus the UDL that we get, WX times X over 2. So our MX will be WLX over 2 minus WX squared over 2. From the differential formula equation, we have EI d square y over dx squared, which is equal to minus mx. In this case, our mx is WLX minus WLX over 2 plus WX squared over 2. That is equal to EI d square y over dx squared. If we differentiate this once, we have dy over dx, which is equal to minus WLX squared over 4 plus WX cubed over 6 plus C1. So we know that when the beam deflects at point A and B, the slopes are not zero. The only place we get the slope 0 is at midspan, which is L over 2. So if we put x L over 2, we will get the slope 0. So 0 is equal to minus WL over 4 times L over 2 square plus W over 6 L over 2 cube plus C1. From here we can work out minus WL square cube over 4 times 4, 16 plus WL the power of 3 over 2 that 2 cube 8, 6, 48 plus C1. We can work out C1 is equal to WL cube over 48 minus WL cube over 16, which will work out to be WL cube over 24. So we have our C1 that we have to put